Hello everyone, I'm Chen, and in this talk, I want to talk about my PhD research on modeling and design enablement for future computing. Let's first look at this scaling roadmap. Since 1990s, we have been start making chips. And at that time, we are still in the geometry scaling era. That is where people directly shrink the channel length to increase the number of transistors on a chip. And we have moved from planar transistor to FinFET to increase the effective width and reduce the short channel effect. And now we are in the 3D scaling area, where we make a gate-all-around transistor that we can stack one transistor on top of each other. And we also use packaging technique and also heterogeneous integration, even monolithic 3D integration to keep increasing the functions and the transistors on a chip. However, the traditional scaling will eventually slow down. Therefore, we need to find some new computing architecture to keep us scale our chips. And one new computing architecture that I'm most interested in is the in-memory computing or neuromorphic computing, which need new embedded non-volatile memories that can be made from new materials such as ferroelectric materials, resistive material, and spintronic materials. The why is memory important? Over the years, the scaling is focused on transistors. We keep making transistors smaller and faster, and so that we actually have quite fast process units. But what actually limited the computing is memory, which is called memory wall. Memory wall is saying that the capacity, the bandwidth, and the speed of the memory cannot keep up with the process units. Therefore, there will be latency between these two units. And when we're trying to move the data between memory and process unit, there will be speed and energy loss. Therefore, that's why we need to introduce new kind of computing architecture, such as in-memory or near-memory computing, and the new memory devices to reduce energy and speed loss in future computing. And what kind of memories we can use for these new applications? For conventional memories, such as SRAM and DRAM, they are volatile memory. That means they need to have a standby power supply to keep the data. Therefore, the standby power is high. And for NAND flash memory, although it is non-volatile, which has low standby power, but we need to make the electron tunnel from the channel to the internal metal gate or either trapping layer, so that we need to use high writing voltages as well as writing energy. And the write speed is also quite slow. That's why we need to introduce emerging memory devices. And in my research, I have studied FERAM, FEFET, STT-MRAM, and RRAM devices. All these devices are non-volatile memories. That means they have low standby powers. And the write voltages, writing energy, and the write speed are also fast comparing to the NAND flash memories. But after we can fabricate all these new devices in our lab, is it already we can start to design new chips with them? Not so fast. We need to have some models that can translate all these device technology and characteristics into something that circuit simulator can run and circuit designer can understand. This is where company models come in. Company models are some mathematical models that mostly use analytical equations to compute device characteristics. Compact models are in contrast to full numerical simulators such as TCAD. Time model use analytical equations to maintain its fast speed. So that when we are trying to run a chip that contains millions or even trillions of transistors, it won't take us forever to do a just simple simulation. And one famous compare model is the Berkeley short channel FEFET model, BSIN. BSINs are the standard FET models that circuit designers have always been used for designing their products. So one of my research is focusing on developing compare models for new memories. So after talking about all these challenge in the energy and the computation for future ICs, there's another challenge in the design itself. As we can see from this figure that the transistor count for the chip now has already go up to 50 billions. And if we do a simple extrapolation, you can see that we will soon go into trillion transistor era. And to do a simulation and design for this kind of transistor is very complex and will take a lot of time. That's why we need to find some way to help us make IC simulation faster, and which is another focus of my research. And here is my outline. First, I will talk about the physics and compare models for future memory devices, including ferroelectric memories, resistive memory, and magnetic memory. Then I will talk about how I can use neural network to build transistor compare model and accelerate IC simulation. In the end, I want to discuss whether neural network can directly be used to do circuit simulations. This is where I propose an idea of NeuroSpice. Let's first talk about ferroelectric memories. Ferroelectric materials are some interesting material that has inherent or built-in polarization or dipole inside its lattice, and which is caused by some dislocation of the atoms. And this polarization can exist even when we doesn't apply any voltage or electric field. So that ferroelectric material can be used as non-volatile memory. And when we apply large enough electric field, we can flip this dislocation from one position to another position to change the polarization stored in this memory to change the stored data. And one advantage of ferroelectric materials is that some of them are CMOS compatible. For example, hafnium oxide-based material. In modern CMOS technology, we already use hafnium oxide as the gate dielectric. And by doping this hafnium oxide, we can make it become ferroelectric material. And another advantage of FE memory is that if we build a device called FEFET, which I will talk about later, and then use FEFET to construct a memory array, we can directly do matrix vector multiplication using this type of memory circuit for application like AI inferencing. And so what kind of device we can make from ferroelectric materials? If we use Fe as a capacitor, we can build FERAM, which is the DRAM type of circuit. And if we build a tunnel junction from Fe, we can make FTJ, that is a memristor type of device. And if we use Fe as a gate dielectric, we can build FEFET, which is a transistor and memory at the same time. And let's first talk about the physics of ferroelectric. The ferroelectric material we are interested in, such as hafnium oxide-based material, they are polycrystalline material. That means in this Fe thin film, we can actually divide it into many small capacitors or grains. And due to the polycrystalline, all these small grains can have different material properties and switching speed caused by the lattice orientation or stress and so on. And then when we apply electric field to this FE thin film, since some of the grains will have faster switching speed, they will switch first and to create this kind of partial switching state. And by using a partial switching, we can actually create multiple memory states inside of FE capacitor. That make FE capacitor or FE devices be ideal for analog memory applications and neuromorphic type of applications. And to build a compare model for FE capacitor, we need to let compare model to compute the correlation for different grains in this FE thin film. And we also need to consider a distribution of the material properties in all these small grains by consider different switching rate. Then after that, we can compute how the red area inside each small grain will change under applied voltages by using this set of differential equations. And in the end, we just need to integrate all these grains to obtain the total polarization of this FE thin film. And so for a good compare model, it has to be able to fit the experimental data. I have verified my FE compare model by fitting it with the QV curve for both ferroelectric and the anti-ferroelectric materials. And you can see that my FE model can model the voltage dependence, including the major loop and the minor loop switching, as well as the frequency dependence of FE and anti-ferroelectric materials. Then I can do a circuit simulation and design with this FE compare model. So here I'm simulate a FE RAM, which is very similar to DRAM. Instead, it uses the polarization in the FE capacitor to store the data, and it is non-volatile. And when we trying to read out the data, we are actually reading the equivalent capacitance in this FE capacitor. For example, if the store polarization is negative, when we read out, we will read out a larger capacitance, which lead to higher baseline voltages. The next FE device I want to talk about is ferroelectric tunnel junction, FTJ. If we can make a device structure that has a metal, ferroelectric, insulator, and semiconductor layer with very thin FE and the insulator layer, we can build a FTJ, which is a main resistor device. That means the resistance of this device depends on the data stored inside its memory. And the operating principle of this kind of FTJ is that let's say we have a polarization look like this stored in the FE layer. It will push up the total potential barrier and reduce the tunneling rate in this structure, which lead to higher resistance. And if we have an opposite polarization, which will pull down the total potential barrier and increase the tunneling rate and reduce the resistance. So to model FTJ, I built up this kind of equivalent circuit, which has a FE capacitor in series with a insulator semiconductor capacitor. And during circuit simulation, the circuit simulator will use KVL to solve these two capacitors and to obtain the voltage drop in each different layers. Then this voltage drop will be fed into a tunneling current model to calculate the total current going through this device. I have verified my FTJ model with the measurement data. And you can see my model can perfectly match the measured current for both on and off state of a FTJ. And I use it to do a circuit simulation for read-write task for FTJ. And you can see if the store polarization is positive, now the potential barrier will be pulled down, which lead to higher reading current. And if the store polarization is negative, now it will push up the potential barrier and leads to lower reading current. The last FE device I want to discuss is Ferroelectric FEFET. By using FE material as gate stack, we can build FEFET that is a transistor and memory at the same time. And similar to FTJ, the polarization stored in this FE layer will change the band structure of this transistor, which is equivalently affect the stressor voltage in this device. So basically, FEFET store the data by using a different stressor voltage under different polarization. And as you can see that FEFET is very similar to NAND flash memory, who also store the data with different stressor voltages. Therefore, one application for FEFET is for future low power NAND flash memory. And it can also be used for this kind of memory circuit I mentioned earlier for AI inference applications. And to model a FEFET device, I use an equivalent circuit approach where a FE capacitor is connected to the gate of a standard FET model such as BSIM. And then I create these two current source to represent the charge on the FE capacitor and the transistor. And by using KCL, this current source will make sure that the charge QFE will be equal to QMOS and ensure the charge equality in FEFETs, which you can see from this figure, that QFE and QMOS perfectly match with each other. Then I verify this model with experimental data. And this model is versatile. It can be able to model different kind of FE devices, different kind of FEFET that has different IV characteristics. I also include models like charge trapping and reverse dip switching so that it can model the inverted memory window and the steep reverse switching in FEFET devices. However, those models are too complicated to discuss here. For anyone who are interested in, you can check my previous paper about FEFET. So far, all the discussion is based on that we have large FE device that has many small grains, and the switching and the memory state can be seen as continuous. But today, we can actually make our device very small. And what will happen when we make our FE device become very small, like just tens of nanometers? Now we can have only a few grains. For example, in this figure, show only 3 grains in our FE device. And if we only have a few grains, now the switching is no longer continuous but discrete, so that we will have discrete memory state. And in order to understand the physics of this kind of nano FE, I conduct a study using time-dependent Ginsburg-Landau simulation. And I build a device structure that has only 3 grains. And then I simulate it and find out that there can be different switching mechanisms inside this kind of nano FE devices, and based on different applied voltages and the material properties. For example, it can have a single domain switching That means like the entire domain will be switched at the same time. It can also have nucleation type of switching, where the polarization start to switch from the nucleus or the defect and then grow out to the entire grain. Then after understand the physics of nano-FE, I want to build a complete model for it. So that I have modified the previous developed FE complete model to consider this kind of discrete switching effect and different switching mechanism under different material properties and voltages. And then here you can see that I have compared the developed model, which are the lines, versus the simulation results from the time-dependent Ginsburg-Landau simulation, which are the dots. And my modified FE complete model can capture the discrete type switching in nano FE devices. Now let's move on to RRAM. RRAM is another promising emerging memory device, which is a man-register type of memory. The advantage of RRAM is that it is quite simple to fabricate. You just need to make this kind of metal insulator metal structure. And the conducting mechanism of RRAM is that when we apply voltages, we can actually create this kind of conducting paths either by metal atoms or oxygen vacancy inside the insulator layer. And those conducting paths or conducting filament will help us conduct currents and reduce the resistance of this RRAM device. Therefore, to model RRAM, we need to understand how the conducting filament grows and then build an equivalent circuit to calculate the total resistance of a RRAM. And people have found out that to model the growth of the filament or the growth or the decrease of this high resistance region, the LH can be modeled by Arrhenius equation. So basically, it's saying that the changing rate of this LH is proportional to the exponential of applied voltage. And then after calculating the LH, we can use it to calculate the tunneling resistance in this insulator region or high resistance region based on the tunneling resistance model. And so after building this RRAM complete model, I have verified it with a metal oxide-based RRAM device. And it can capture the multi-level switching and the set and reset process of this OX-RAM device. And the key new feature of this new model is that it is versatile and universal. It can not only model metal oxide-based RAM, it can also model conducting bridge RAM and the hybrid RRAM device that exhibit both the characteristics of CB-RAM and OX-RAM. The last memory device I want to discuss is STT-NRAM. NRAM is kind of different from FE or RRAM devices. In NRAM, we have two layers. One is the reference layer where the spin does not change, and another is the storage layer where the spin can change. And NRAM basically store the data in the spin of this storage layer. And as we know that the electron spin just have up and down. Therefore, NRAM is mostly for digital applications. And the conducting mechanism of NRAM is that, let's say now we have the same spin for both reference and storage layer. And when electron want to tunnel from the reference layer to the storage layer, now it will see the same density of state. So it can easily fill into the vacancy in the storage layer, which has higher tunneling rates and lower resistance. Now, if this two layer has different spin, when electron trying to tunnel from a reference layer to a storage layer, it will see a different density of state. So it will be harder for the electron to fill into that vacancy and leads to lower tunneling rates and higher resistance. And for the NRAM device I'm studying, which is STT NRAM, in STT NRAM, electron can use so-called spin transfer torque to carry spin torque from the reference layer to the storage layer, and use that spin torque to change the magnetization in the storage layer and change the stored data. And the advantage of NRAM compared to FE and RRAM is that it has better endurance. And people has known that the most physical way to model NRAM is using 3D Landau-Shifley-Gilbert equation. However, it is not efficient and quite time-consuming to solve this kind of time-dependent differential three-dimensional equation in circuit simulator. Fortunately, for the NRAM device that most people are interested in, which is the perpendicular NRAM, we only care about the magnetization in Z direction. Therefore, we can simplify 3D LLG into 1D LLG equation and give us a 2.5 times of speed up in circuit simulations. But this simplification can still keep the essential physics of STT NRAMs. Here I'm comparing the simulation result of this model versus the full 3D LLG simulation. And my model can accurately capture the switching current as well as the magnetization change in this NRAM device. But it is not enough to just verify the model with LLG simulation. We also need to verify it with the experimental data. In the left-hand side figure, I use this model to calibrate the post-width dependence of the critical current for STT NRAM devices. And this post-width dependence is saying that when we apply higher current, we will actually be able to switch our NRAM device faster using shorter post width, and which can be captured by my NRAM model. I also calibrate the model to the measured read-write operation for a STT NRAM device with perfect match. And I have talked about many new memory devices. But transistors still remain the major part of ICs. As I have mentioned, today the transistor count has already gone up to 50 billions. And it might take a lot of time for us to simulate this kind of chip. During my internship, I got a chance to simulate a subsystem in a chip, and it can already take 4+ hours to do that. And for a full chip simulation, it may go up to 1 day or even more. So we need to find some new way to accelerate IC simulations. And since the transistor is the major part of the chip, I'm thinking that we can first start from accelerate the transistor modeling. And the problem of the transistor model these days is that as we keep shrinking transistors, more and more side effects, shortening effects, non-idealities will show up, and we need to consider them in the model equations and codes that's slowing down the IC simulations. So one solution I have been looked into is using neural network to replace all these complex physical equations with efficient matrix multiplications to speed up IC simulations. And so this is where I developed a model called BSynNN. BSynNN use artificial neural networks to model and learn the input-output relationship of field effect transistors. So in my BSynNN model, it contains two networks. One is to calculate the charges, and another is to calculate the currents. The input of this network can be the device bias condition, device parameters, temperature, and so on. And the output can be the terminal charges and terminal currents. My BSynNN has shown very high accuracy in both DC, IV, and CV characteristics. It accurately model them in different bias conditions and different geometries. However, for a complete model, only a DC or the so-called quasi-static modeling is not enough. We also need to consider high-frequency effects. This is because that the quasi-static assumptions fails when the operating frequency of devices close to cutoff frequency. At this point, we can no longer assume that charge will instantaneously show up in the drain end. We need to consider the time for the carriers to transport from source to the drain, which is the transit time. And to model this kind of transit time effect or non-quasi-static effect, I use a hybrid approach to combine an NN model with the physics-based charge deficit model. So what this framework is doing is that the neural network will compute the quasi-static current and charge, and those charge will then be fed into a charge deficit subcircuit. What this circuit do is that it will add this transit time delay to the charge to mimic the NQS effect. And to validate this NQS model, I do some circuit simulation and compare it with the standard Bayesian CNG results. And I have done some simulation like a common source amplifier and a NOR gate. And all the results have showing all the results can match the Bayesian CMG without any unphysical behaviors. And in my BSynNN model, I also include self-heating modeling. Self-heating is a serious issue in modern-day ICs, where during our device and circuit operations, the temperature goes up, and which will degrade transistor and the circuit performance. And using neural network, I can actually invent a new type of self-heating model that I called it a temperature realization model. And what this temperature realization model does is that it will introduce an artificial temperature TINA prompt to the neural network model. And during the circuit simulation, I will use this subcircuit to calculate the change of TINA prompt. And for example, if we give a voltage pulse to our transistor, we know that at the beginning of the time, since the heat hasn't accumulated and device is in lower temperature, we'll get higher device current. And to mimic that, this temperature realization model will do some kind of reverse engineering to try to recover the intrinsic characteristics without self-heating by pointing this TINA prompt to some lower temperature to mimic the higher current at the beginning of the pulse. And then after that, TINA prompt will gradually increase, which is similar to the ordinary device temperature, and to the point that the device characteristics will go back to its DC ambient condition, including the self-heating effect. And the good thing or the advantage of this new model is that we can only train our neural network model using DC measurement data that includes self-heating. So no spatial measurements such as post-IV measurement is needed to exclude self-heating effects from the data. And then to verify my NN model under self-heating and the different temperature, first I have test this model at different ambient temperature, and it can model the temperature dependence of a transistor very well. And then I do a transient simulation by applying multiple pulses to a transistor. And you can see that at the beginning of the pulse, this temperature realization model can make the device current go to a higher value that is where no self-heating effect has exists. But after that, the self-heating will begin to increase the temperature of the device, and the device current will go down to its DC ambient value, which can be captured by my temperature realization model. My Bayesian NN model also includes noise, which is an important part in analog and RF circuit designs. I introduced simple empirical equations to Bayesian NN to calculate noise such as thermal noise, flicker noise, and so on. And I use it to do a SPICE noise simulation. And you can see that my noise model can accurately capture the frequency dependence of output noise for a common source amplifier, as well as the phase noise spectrum for a 3-stage ring oscillator. I also test this model with more complex circuits, such as 151-stage NAND oscillator and a 32-bit ripple adder. And all of them show accurate results without any convergence issue during circuit simulations. And one of the goals of this research is to speed up our IC simulation. Therefore, I have tested different benchmark circuit using my Bayesian NN model and the Bayesian CNG model. And overall, there is 3 to 5 times of speed improvement by using this Bayesian NN model. So you can imagine that if we have a simulation that originally needs to take 5 hours to do that, with this Bayesian NN model, it is possible for us to reduce to 1 hour. That can greatly speed up the IC development time. And so far, I have discussed using AI to accelerate device model for IC simulations. But what else can we use AI to help circuit simulations? And this is where I have found out a new type of neural network that is called physics-informed neural network, which can directly be used to solve differential equation without any training data. And can we use PIN to do circuit simulations? So this is where I come up with this idea of NeuroSpice. Conventional circuit simulators such as SPICE use numerical methods to solve circuit equations with discrete time steps. However, NeuroSpice or like the PIN, they use a different approach to solve differential equation by mapping them to the loss function of this neural network. So what it does is that first we got this circuit, and we can obtain the differential algebraic equations from this circuit, and we map this equation to a loss function of NeuroSpice. And during the training algorithm will try to minimize the loss. In this case, it will minimize the residue of this differential equation, which is equivalent to solving it. And the interesting thing of this NeuroSpice is that it is trying to approximate the final solution with a continuous function. And it does not need to solve the circuit at each discrete time step. It can solve the entire time range at the same time. So which can possibly help us to speed up the circuit simulation. Using this NeuroSpice, I have tested with some simple analog and digital circuits such as non-inverting amplifier and a ring oscillator, all of them showing accurate results. This NeuroSpice is also quite flexible. It can be applied to emerging device and emerging circuits. For example, here I'm using NeuroSpice to simulate a FERAM circuit where the FE capacitor is described by this kind of FELK model, which is a highly nonlinear model, and it's kind of difficult for ordinary numerical solver to solve that. And in my NeuroSpice, it can solve this kind of highly nonlinear device equation without convergence issue and give us accurate results. However, at this point, the performance, like the speed of the NeuroSpice, cannot compete with the commercial Spice, which has been developed and optimized over the years. Therefore, further research is needed to help us keep improving this NeuroSpice to make it to a production level. And maybe people can also find some way to combine NeuroSpice with commercial Spice to improve the circuit simulation. In the end, I would like to thank my advisor, Professor Hu and Professor Salavuddin for their guidance, and my my dissertation prelim committee and the qual committee for their advice through my PhD journey. I also would like to thank all the co-authors for my work. Without their work, I cannot produce all these research results. And here is the publication list. And if you are interested in any of the topic I mentioned, you can check those papers to find out more details. Thank you.